let's start here and let me do my best today to stick close to the machine so that the tape sound on the tape will be better. And people are going to look at the tape because we got people missing. Not a good time to stop coming. Actually, worst possible time to stop coming. But okay, um, their tuition. Um, uh, we I want to look at, so we have a homework that was due tonight, this one on iterated integrals and areas in the plane. So, but I want to look at some problems from that because just a few, because I'm reminded that it's one thing to set up the double integrals, right? So that already might be conceptually challenging, but there's no real computations to do in setting, or very few, in setting up the double integrals. Maybe a little bit of algebra when you're thinking about the region of integration, right, and the boundaries for the region of integration. Sometimes that requires some algebra, but then after you set up the double integral, if you have to evaluate that double definite integral, of course that involves integration, right? So, and sometimes that's hard. Okay, in fact, frequently that's hard, right? So and so I sort of forgot that we're going to have challenges with integration as well. Okay, in some of these homework problems. So if you haven't started on this one, some of them are going to be tricky. All right, and may force you to recall some of your integration skills. Okay, so if you're good at that, that's great. But usually no one is that good at it that it goes off perfectly smoothly without a hitch. So we're going to look at a couple of those problems, but it's nice cold weather, so that's great weather for integration, right? Okay, because what else do you need? So you got plenty of time to spend evaluating a definite integral, one that might involve integration by substitution and then integration by parts, right? I can remember all your favorite integration techniques. I hope there's no partial fractions. See one so far that involved integration by partial fractions, but I know that lurking here somewhere are probably some problems that involve trig substitution. So that's not fun. And then also um, uh, infinite integrals, right? Where you have to use a infinity as a limit of integration. Okay, so have to remember how to do those sorts of things too. Maybe. Okay, so if you have an unbounded region that you're trying to integrate over. Okay. Well, so after I've scared you there, now let's look at just a couple of these problems here from this homework that was due tonight. So I pushed that back a little bit, and we can push it back even more if it's going to be slow going. So these are the notes that we were looking at last time, but these are about volumes and double integrals, not about regions in the plane and double integrals, although those things are closely related. But those are the problems that I was thinking about, at least commenting on from this homework. So let me open that and let's look first there at problem number 4. Okay, so it just says evaluate that iterated integral. All right, so that's not really a conceptual problem. You don't have to set up the iterated integral, right? We're just evaluating that. Okay, so it looks pretty innocent there, right? To start with, but when we get into it, right, then that's when it may get a little bit more challenging. All right, so let's so y'all remember that for me? Can y'all write that down? So because I've got to switch back to the notes there, and find some blank paper here for us to at least start this one on, so we can see what we're up against here. All right, so let me let's lower the screen here so I can write more easily. So what was that double integral? Let's see. That outer integral, the limits of integration were 3 to 5. I remember that much. Okay. And then for that inner integral, right, it was what? 1 square to the square root of x, right? Okay. So so that must mean that y is varying, right? On this inner integral. So that's dy, is that right? And then dx is the outer variable for integration there, right? Okay. And now what's that integrand? So for most of these, right, where we're just computing the area of a region in the plane, the integrand is going to be 1. But for this one, they didn't tell us what the application of this double integral was, right? So it doesn't have an integrand of 1. It was something like 2 times y times, what was it, e to the minus x? Okay. So so again, that looks pretty easy to start with, right? So you work inside out, right? Just following the order of operations here, kind of, although there's no parentheses in the expression. So we're going to try to evaluate that that inner definite integral first, right? And then once we have some expression there, right, we'll use that as the integrand for our outer definite integral, right? So remember now, we're integrating with respect to y here, right? Okay, so y is the variable, so that means that e to the minus x there, right? Just a nice constant, right? Okay, so that makes things kind of easy there to start with, right? So we just get what just preserve that outer definite integral, right? And then just integrate this expression. But that's easy, right? Because you just have your 2y to the first power. So how are you going to integrate that? The anti-power rule, yeah, what I call the inner power rule, right? So that's so easy. So don't even have to do any substitution or anything, right? Just use the anti-power rule. So just add 1 to the exponent, right? Divide by the new exponent, and the e to the minus x, right? That just hangs around as a that's just going to hang around as a constant, correct? And now we're going to evaluate, right, our antiderivative. This is the antiderivative now, right? So we're going to evaluate that antiderivative from 1 to square root of x, right? And then once we finish that, then we have the second integral, right, integrated with respect to x, okay? So let's see, what does this come out looking like? So it's getting a little bit messy, but maybe it's not horrible yet, right? Of course, these 2's are going to divide out, so that's nice. So they made that easy for us, right? And now we're plugging in what, square root of x for y. So you're just squaring the square root of x. So I guess that just gives us x, right? But don't forget that's multiplied times this e to the minus x. And then let's see what happens when we plug in 1. That's even nicer, right? Because we just get 1 squared. So I get e to the minus x here, right? And so that's our integrand. I guess if we want to, we can put it in parentheses. If we space carefully, we can avoid the parentheses. But now we're integrating this from 3 to 5, right? Okay. Now that looks more. It kind of looks more palatable because that looks like a calculus 1 problem, correct? Right? Just a regular old definite integral calculus 1 problem. So we know we can integrate term by term, right? We can integrate term by term this integrand because we have 2 terms here, right? Terms are quantities that are added or subtracted. So I can integrate this one and I can integrate this one. So let's actually split that up then. You may not have to, but you might be able to find the antiderivative just directly, right, without splitting the integral up into 2 integrals. But I'm going to split it into 2 integrals because I'm kind of looking ahead here and seeing that we're going to have a problem with this term, right? Because that's not so easy to integrate. This is not so bad to integrate, okay? Right? Just integrating e to the minus x, not so bad. So I think this definite integral will be easy for us to compute. By the way, how would we how would we do this? This second part. Let's do it let's do it a little bit off to the side here. We could do it all all in one equation, but just make it easier to understand. Let's do it off to the side here. So how would we integrate this? What technique would we use? Perfect, right? You're going to use integration by substitution. If that were just e to the x, that would be easy to integrate, right? Because what's the antiderivative of e to the x? The antiderivative of e to the x. It's e to the x. Okay, so if that's just e to the x, it's easy. So we want to make this look kind of like e to the x, right? So we do that by substitution. You're exactly right, David. So let's see, how does that work? You might have to remind me here. So I'm going to let u be e to the just minus x. Is that right? So I'll end up with EU here, right? And then we have, so then we take the derivative of this, right? So what's du dx? That's easy. -1. So that means dx, which is what I have in my expression here, right, is going to be, is that minus du? Is that right? Yeah, okay, right? See, I'm solving for dx there, right? Because I need to, I'm going to get rid of the minus x. That's easy, that's u, but then I also have to get rid of the dx, right? So so let's skip over here by let's skip over here my substitutions and write what we have. Now, technically, I should change the limits of integration, right? Technically, I should change the limits of integration, but I'm not going to change those because that just create the limits of integration have changed here because I've switched variables. But I'm not going to change those because it's going to make me have more work. Because in the end, I'm going to go back to x anyway. All right, so I'm just going to leave these original limits of integration here. All right, and so let's see now. I have what e to the u what now? Oh, and dx is du, but there's a minus sign there, correct? So so let's be sure to put the minus in there. So here's what I'm integrating, right? So you can pull the minus sign out in front, of course, and now you have exactly what you kind of want to deal with, right, David? So how does that integrate? You already told me. Yeah, it's just e to the u, right? Right. Okay. And now I want to get rid of the so let's keep the limits of integration here, right? But now those are the wrong limits of integration, right, for the u. But I can fix that just by going back to x, right? Because what is u? Is that minus x? So I have here e to the minus x back to x, right? Evaluated from 3 to 5. So that looks like, well, I really can't, I mean, I can do the substitution. I really can't do much simplification with the arithmetic, right? But so I have what, minus e to the minus 5, and then minus, what, a minus e to the minus 3. So I end up with 2 minus signs there, right? As of course, you have to subtract by your sign. So that end up looking that this is positive. That's 1 over cubed. So it looks like 1 over e cubed minus 1 over e to the 5th. If I can squeeze all that in here. 1 over e cubed minus 1 over e to the 5th power. Did I make a mistake there? Are the signs right? Now y'all got to help me, okay? Because I make mistakes too, right? So if y'all aren't watching me, then we're just going to end up with possibly here with a big mess here, right? Okay. So stay engaged there and make sure that I don't make some sort of arithmetic mistake. All right. Okay. So, all right. That was hard enough, right? But that's only half of it because I still have this darned definite integral to take care of. That one is tougher because of the x. So because I have x e to the minus x. That I'm not going to be able to do by just by straight substitution. All right. So I need some other integration technique to help me with this. Okay. Y'all have any suggestions for that one? Integration by parts. Yeah, that's kind of the classic integration by parts situation, right? Okay. Um, so we're going to try integration by parts. So let's see, how does that integration by part? Oh God, I have to remind myself of the integration by parts formula, right? So integration by parts said what? If you're trying to integrate what? U dv, right? So U is some expression, right? Okay. Then that's equal to what? U times V, right? Minus the antiderivative of what? V du, right? Okay. So remember, this is the famous integration by parts. Y'all know where that comes from, right? Yeah. Okay. That is the anti-product rule. All right. That is the anti-product rule. You know, the product rule is a popular rule, right, to help you with computing derivatives, right? Okay. But if you run the product rule in reverse in just the right way, you get integration by parts formula. Okay. So it's the anti-product rule, just like we use the anti-power rule here, right? Okay, to compute that integration by parts comes around from reversing the product rule. I don't know what you get when you reverse the quotient rule. Yuck. Okay. But the quotient rule is really just the product rule in disguise anyway, right? Okay. So we need to, so what we're going to have to try to use here, and I hope you recall, well, many of you did, we're going to have to use here integration by parts. Okay. And that's a standard example, x times e to the x. This is just a minus x here, but x times e to the x, that's a standard example of integration by parts. Now the question is, what's going to be the u and what's going to be the dv, right? Okay, because you have three factors in this expression. You have x e to the x, and then you have dx here, right? Okay. Do you remember when you're using integration by parts, there's a little shortcut that can sometimes help you figure out, doesn't always work, but sometimes helps you to figure out what to choose as u in the integration by parts formula, and then the rest becomes dv. Okay, so I think that rule is an acronym, and it reads like this. It's Li8, and I'm writing the acronym there in that order because this is an acronym. So the L stands for log. So if you have a log function in your integrand and you're going to try using integration by parts, let u be the log function. All right. First, choose that as u. Okay. That's your first chart. Can you all imagine what I stands for? Yeah, that's inverse trig functions. I guess it could be any sort of inverse function, but it's always usually a trig function. So if you have an arc cosine or an arc sine or something and you're trying to integrate it, sometimes integration by parts quite useful. Okay. And it's useful to let, in this priority, let u be the inverse trig function A, algebraic, right? And then, T is trig, and then E, that's exponential. Notice that's lowest priority. So we're not going to let u be e to the minus x. I can tell you that. All right. That's what this rule of thumb is telling us. So so what will we let u be? Yes, because that is algebraic. Algebraic means things like polynomials, right? Addition, subtraction, multiplication, division of just your variable, right? Your variable of integration. That could also include like square root of your variable of integration, right? So so I think here we're right. We're going to let u be x, and then whoops, come back, machine. We'll let u be x. If I can get this to I get my pen turned back on here. Yeah. All right. So let's let u to the x. So now we have to go through all of this. So what's dv? That's going to be the rest of it. Yeah. So that's e to the minus x dx. And then du. 1. Yay. Okay. Right. And now we have to figure out what v is, of course. But how do we figure out what v is? We integrate dv, right? Okay. So just find v by integrating dv. So you integrate e to the minus x dx, right? But that's so easy to integrate. That's just e to the minus x. So can y'all see what that's going to be? I think it's going to be minus e to the minus x, isn't it? Because if you can do this by substitution like we did down here, but I think by inspection you can see the antiderivative of e to the minus the antiderivative of e to the x would be e to the x, right? So the antiderivative of e to the minus x, well, it's going to have a minus sign in it somewhere, and I just put a minus sign in front. If you differentiate this minus e to the minus x, you'll get e to the minus x. All right, so there's v, and so now you can fill that in to your. Now you can fill that into your integration by parts formula, right? Notice when you do that. So for this, let's just find the antiderivative first. We'll worry about the limits of integration later, right? So if we're finding the antiderivative of x e to the minus x dx, according to our formula, that would be what? That would be u, which we said was x, right? Times v, which is minus e to the minus x, right? Minus, and then now we still have to find another antiderivative of v, right? Which is what? Minus e to the minus x, right? And then du, though, but what's du? Well, really, it's 1 dx, right? Okay, I left the dx off there when I took the derivative, right? There you have it. Now, so you still have some work to do here, right? Because you have to find this antiderivative, but now that's easy, right? Because you're really just finding the antiderivative of minus e to the minus x, right? And so that you can do just pretty easily there by substitution. Actually, we sort of did that already without the minus sign, right? Earlier, correct? Okay, so so you can easily integrate this, right? Then you will have your antiderivative, and then you just fill in your limits of integration 3 and 5, and then put those back in here, right, into your original definite integral. So we knew what this one was, right? We calculated this. Now we can use our integration by parts, right, to calculate this definite integral. And we're going to come up with a lengthy expression. So I'm not going to finish that one for you, but that's what you have to do in that case. Now, look, there may be times now where you get stuck, okay, in the integration, okay? And sometimes it might be a legitimate reason for, sometimes there might be a legitimate reason for getting stuck. It may be just a really difficult antiderivative or integral. So you can make use, I'm encouraging you sometimes if you need to, if you get stuck, make use of Wolfram Alpha, because Wolfram Alpha is really good at integrals. So I want to show you how to do that now. Let me flip the screen here for a minute, though, so I can type. Because if I'm checking there on the keyboard, we will be a long time. All right. So the command in Wolfram Alpha for integrating is just exactly what you would expect. Remember, this is a command line interface, so it's just going to be integrate, all right? But we have a double integral. So we're going to integrate an integral. So for the double integral, you're going to integrate and then you're going to integrate again. So for that inner integral, put that in parentheses, okay? So let's see if we can type in what we had there. So what was the original double integral? It was, we wanted to integrate what? What was the integrand? Wasn't it y times something, right? Y or 2y, I'm sorry. Wasn't it 2y e to the what? Negative x. So on the command line, you know, you can get the exponent by using the caret key. So that's 2y e to the minus x. That's what we're integrating. That's the inner integral. But we need the limits of integration, right? So what are the limits of integration there? Yeah, from what y equals what? What did it start with? 1, right? To y equals square root of x. Here's how you get square root. It's just, you have to use this function, sqrt. You could put x to the 1/2 too, I think. So x caret 1/2 would also work here. Remember, y is the variable integration. So you're integrating from y equals the lower limit, which is 1, to y equals the upper limit, which was square root of x. Right now, that is the inner integration, right? What are the limits of integration for the outer one? So that's from what? X equals what? 3, right? To x equals 5? So I think I'm hoping this command will give us the right answer there. Let's see if we got enough parentheses in there to do it. Oh, there it is. Oh, and it gives us pretty printing there. That's nice, right? Is that the right integral we were trying to do? I think so, correct? Did I actually type that correctly? Yeah, and so there, ultimately, when you simplify the result, there's what you get. It's 2 e squared minus 5 over e to the 5th power. Okay, so you're gonna have a bunch of terms there involving e. I think e powers of e in the denominator. When you add all those together, you end up getting this. Okay, 2e squared minus 5 e to the 5th power, right? So if you just have run out of tricks in your, in your bag of integration tricks, then you can try using Wolfram Alpha. Do you see that command? So it's integrate. That's just the basic integration command from lower bound to upper bound, right? And then, but if you have a double integral, right, you're going to have to integrate inside of that outer integration command. This will come in handy because we are going to have some challenging integrals in your homework. And if you get stuck, just can't, you can set up the integral, but you can't carry out the integral, then try using Wolfram Alpha, okay, to help you get unstuck. All right. Well, let's see. We may get to use that one again. Let's see what the next problem is. If I can find that homework. Shoot, where is that thing? Is there a similar acronym? Wait. Yeah, that's right. So you find U, and then the rest of it is the rest of it is dv, right? Okay. Remember, the dx always goes with the d, of course, because the dv is the derivative, right? So the dx always is incorporated. The dx that's in the integrand is always incorporated into the dv expression. That's kind of a formality, except you have to integrate to find v, right? So technically, you need the dx to do the integration, but that's kind of just as I mentioned, just formality. Let's see. Let's reopen this one. I think I lost it there. Oh, no, I didn't. Ooh, let's look at this one then. Maybe the same thing. Okay. Wow. All right. Oh, it has cosine in it. That already is making me nervous, right? But actually, the double integral itself, right, is not it doesn't look too intimidating, correct? Okay. I mean, you can read it easily. So it looks like something that at least we can get started with, right? Carrying out. So can you write that down? We're going to see integrals like this shortly because um, some double integrals are easier to compute by switching to polar coordinates. So polar coordinates are getting ready to show up also. Um, and but and when you switch double integrals to polar coordinates, um, sometimes they come out looking like this. Okay, so that may be a double integral derived from polar coordinates. But of course, we don't need to know that, right? Just to start trying to evaluate that. So let's see if we can write that one. See if we can write that one down also. All right, so let me, my writing here now is going to first thing. So let's see, what was that? What was the integral was going from what to what? 0 to, yeah, it has to be something pi, right? So 0 to pi over 2. And then the integral, the inner one was 0 to 10 cosine theta. But the integrand was easy, right? It was just r, and then what, dr d theta? That makes sense because notice you have theta in this upper limit, right? So that means theta has to be a constant for this inner integral, which means your variable of integration has to be r for the inner, right? And then for the outer integral, going to be theta. All right. Well, this doesn't seem like it should be all that bad, right? Because what's the antiderivative? What's the antiderivative on the inside there? If you integrate r, you can just use the anti-power rule, right? So that's just what, r squared over 2, right? Evaluated from 0 to, that's the bad part, 10 cosine of theta, right? And then d theta. So wow, we're going to end up with some big coefficients here maybe, but even worse than that, what do we end up with? I think a cosine squared, right? So you plug 10 cosine theta in for r, and you have to square that. So you have 10 cosine theta, all of that squared over 2 for what it's worth, right? And then now we plug in the 0, right? Okay. Well, that's nice. So that's 0 squared over 2, right? Guess I should put some extra parentheses here just to break things up a little bit. Okay, well, the 0 squared over 2, I'm happy with that because that just becomes 0. But this is the one that's, this first term, of course, is the one that's ugly. So 10 squared is 100, divided by 2 is 50, which isn't the most pleasant coefficient, but not terrible, right? But the second part here is what's bad because you have to square the cosine. So you get cosine squared theta. Yuck. And now I have to integrate cosine squared theta. Oh my God. So now I'm having to remember how to integrate powers of cosine. You cannot just use substitution here. I think the natural inclination, right, would be try to use substitution and then use the anti-power rule, correct? Because you have an expression raised to a power. You know, when you have an expression raised to a power, not x, not just x or the variable, in this case theta, raised to a power, right? You usually want to use the anti-power rule, but if the expression is more complicated than just the variable, you'll have to use substitution, right? So my first inclination would be say, let's let u be cosine of theta, because then this would become u squared. And then I think I could just maybe use the anti-power rule to integrate u squared, right? But the problem with that is you have to get rid of d theta. And so you have to compute du d theta. What is du d theta? So what's the derivative of cosine? It's minus sine theta. See, and see, things are going awry here now. So when you solve for d theta, you get what? Du is, I'm sorry, d theta is what? Du over minus sine theta? I'm skipping some steps there. Du over minus sine theta, right? That's d theta. And so I plug that in. So I get something like this, and this is not very satisfying at all. So I do get u squared. See, u is cosine, so I get u squared. That's okay. But the d theta is unfortunately du over minus sine theta, and that is not what I need, because I have now two variables. And I'm not going to be able to integrate that, right? I needed to get rid of the theta and just get left with the u. If I had 50u squared du, then that would be in great shape. I could use the anti-power rule. But unfortunately, the minus sine theta is still hanging around there, so that screws things up. Phooey. All right, so it's back to the drawing board. Just forget all of this. That was all useless. And have any other ideas? Do you recall how anything about integrating powers of cosine? Did you all do that? Yeah, you can use a trig sub, but for cosine squared, you get a little bit of a break. Okay, so normally powers of cosine are going to be challenging, but with cosine squared, you get a little bit of a break because of trig. Do you remember? I think there's a you've probably forgotten it, but I think there's a nice handy identity for cosine squared. That's exactly what it is. It's 1 plus cosine of 2 theta over 2. So you can replace the cosine squared theta by this identity. And that now makes everything work. So we get, let me take the 50 out, because that 50 is annoying. So let's take the 50 out. And so I get 1 plus cosine of 2 theta, which is over 2, which is cosine squared, right? Well, I guess I could take the 2 out also. And then we have the d theta. So you can factor out the 2 also and just get 25. And then 1 plus cosine of 2 theta. So you get two terms there, but I think both of those terms are now easy to integrate. Of course, how do you integrate one? That's theta, right? Okay. But Robert, are you going to integrate cosine of 2 theta? That's cosine of 2 theta. See, if it were cosine of theta, what's the antiderivative? Yeah, it's minus sine theta, right? But this is cosine of 2 theta, so I have to do a little bit of extra work. What? Yeah, use a substitution. So let u be 2 theta. Okay. So to integrate the 1, that's just theta. So, but for cosine 2 theta, let u be 2 theta. So du d theta becomes just 2, right? Which means now d theta is, what is that, du over 2? So nice. Now you can substitute in u, right, for 2 theta. And then for d theta, just put in du over 2. And then you'll be in business there. So then now you can continue integrating that. Okay, so I think from that point on, you can handle, I think from that point on, you can handle that one. Do you want to try that with Wolfram Alpha? Let's see what, I'm curious to see what Wolfram Alpha does with this. So what's the integrand there? Oh, that's so easy. Just R, right? So can y'all remember that for me? Let's switch back here to our integration command. Ooh, once I've got this typed in now, I can sort of just type over it, right? So what's in my inner integral there? It's just R, correct, right? From R equals, is that right? Was it R? Yeah. R equals what? 0 to, what was that? 10 cosine theta? 10 times the cosine of, and I think theta, you can just type it. So that's theta. Just type out the spelling of theta, which is this. And then let's see, what's the range of theta then? It's going from, what was that, 0 to pi over 2? Let's see if it will do this for us. I didn't check this one, so I'm not sure what's going to happen here. And just again, just spell the Greek letter pi, which is pi, divided by 2. Does that look like that has a chance of being right? Let's see. Wow. Is that the right double integral? I think it was, yeah. See, that's the nice thing here. You can check your work in Wolfram Alpha because it prints out so beautifully, right? So that is the right double integral, correct? And it turns out to be, kind of not surprisingly there, just 25 pi over 2. So if you forgot how to integrate cosine squared, which is not unusual, okay, I have to remember that every time I see it, how that works. Just try Wolfram Alpha, okay. The key thing is going for us. I'm not going to say it's the key thing, but a really important step for us is going to be not always computing the double integrals, but it's setting up the double integrals, right? Ooh, well, speaking of which, okay, let's go down again a little bit in the homework and see if we can do this. Okay, so here we want to find, this is not a volume, right? We're getting to volume problems, but here we want to find the area of the region, okay? So we want to use a double integral to find the area of the region. So remember, you need to have you're hoping to have a vertically simple region, right? Or a horizontally simple region, right? In order to calculate its area by using a double integral. But remember, when you're computing the area of a region, the integrand is easy. It always just turns out to be what? 1, right? It always just turns out to be 1. So you can see the integrand here they've given you because it's trivial is just 1. All you have to figure out are what the limits of integration are. So to do that, you need to look at you need to at least visualize in your mind, or if you can't visualize in your mind, try sketching it on paper what the region of integration looks like, right? Because you want to make sure that that's either horizontally simple or vertically simple, right? And then if it's one of the two, maybe both actually, then that can tell you what the limits of the integrals are going to be in your double integration, and then also what the order of integration is going to be as well. Okay, is it going to be dy dx or dx dy? That's sometimes important because the order of integration sometimes makes a difference in how easy it is to compute an integral. That is important. Theoretically, either order will give you the same answer, but computationally, both orders are not always the same in terms of difficulty. All right, so let's try sketching this and see what that let's try sketching this and see what that looks like. So I need it, but we're just going to make a rough sketch, right? We don't have to have a beautiful sketch here of this. So let's go again, find some paper, and I'm just trying to make a simple sketch here of those two curves, just so I can see what this this is going to be messy because I'm trying to write here with the screen upright. So let's see, what was the first curve they gave us? Was it what, 36 minus x squared? What is that? That's a parabola, right? And Fatin, what does it look like? Just in words, what does it look like? It's facing down, right? What's the y-intercept? Way up at 36, right? Yeah, the y-intercept is way up here at 36 because when x is 0. So you're way up here on the y-axis, so this is not going to be drawn to scale. What are the x, and it's going down, right? What are the x-intercepts? Yeah, that's easy to see, right? The x-intercepts are going to be 6 and minus 6, right? If you set y to 0 and solve for x, you'll get 6 and minus 6, right? So there are your two x-intercepts there, one at minus 6 and one at 6, and this points down, so this region, I'm sorry, this curve, which is going to be one of the boundaries of the regions, right, looks like this, right? Now, what was the other one? I forgot. X plus 6 or something? Was that it? So what is x plus 6? That's obviously just a straight line, right? Okay. Crosses the, this is 36, crosses the y-axis here at 6, right? So the y-intercept is 6. What's the x-intercept there? Minus 6? Down here? Right there? So it's a straight line? So like this? Oh, so what's the region? It's got to be bounded by these, correct? Oh, so it's this piece in here. So is that a simple region? Yes. Which direction? Elijah, what? Yeah, it's vertically simple region, right? Okay. Vertically simple region, correct? Vertically simple region. That because that is just bounded above and below, right? By the two curves, one curve on the bottom and one curve on the top. Okay. So remember, for a vertically simple region, right? What's the order of integration going to be? Is it dy dx? Yeah, I think that's right. Okay. Because am I thinking of this properly? Right? You want a function of y here on the bottom and a function of y here on the top as your limits of integration, right? Okay. So what's the I'm sorry, not a function of x, right? Y equal to a function of x as your bottom limit of integration, y equal function of x as your top limit. Um, what is this bottom limit then? What's the curve here? What? X plus 6, right? And what's the top there? 36 minus x squared, right? So you don't have to write the y equal, right? You would just have x plus 6 and 36 minus x squared. The y equal is understood, right? Remember, the integrand is 1. And then what about for the limits on x? Is that this point here? You have to be careful. Clearly, it starts here at minus 6, correct? But where does that region end at? That's the part that's a little bit confusing, right? So what is this point, in other words, especially on the x-axis, right? Because that's what we need to know. Um, that's right, where they intersect each other. And how do you find that? Set them equal to each other, right? So you have 36 minus x squared is equal to what? X plus 6. So what happens here? Shift them all over. So I have x squared plus x minus 30, right? Is equal to 0. We can solve that by the quadratic formula if we want to, if we insist on it. But I think this factors. Doesn't this factor as, am I doing this right? X plus 6, oh yeah, times x minus 5. Well, yeah, it does factor. Oh, nice. Okay. So we can see what that the two solutions here to the equation are what? Minus 6 and positive 5? Oh, so this is 5 on the x-axis. So just get a 5. Okay. So there's the double integral that gives you that region, right? See, of course, when you evaluate this double integral, it's easy to see what's going to happen, right? Since your integrand is just 1, right? The antiderivative of 1 is just x. I'm sorry, is just y, because we're integrating with respect to y. And we're going from x plus 6 to 36 to 36 minus x squared. So you end up, of course, exactly what we would expect, right, for computing the area of that region, just taking the difference of these two functions, correct? The upper function and the lower function. So you get 36 minus x squared, and then you're subtracting off from that x plus 6. And you know from calculus 1, right, that's how you find the area of the region between two functions of x, two functions of x. Okay, so again, now it's easy, right, to carry out the now it's easy there, right, to carry out the definite integration. Let's look at one more, the very last one. So here we're not computing the the area of a region. So our integrand does not turn out to be 1, right? Okay. We're computing something. So this is probably some sort of volume, right? Okay. But here is the region of integration in the XY plane. Okay. Well, one of these is the region of integration in the XY plane. And we're trying to figure out which is the right one, right? So we have to look at you don't really care about the integrand in that case, all right? So you don't need to look at the integrand. What you're really looking at there are your limits of integration, right? And sort of interpreting those limits of integration to draw that to pick that correct region. So let's see which is going to be which is going to be the correct one there. So maybe best to start with the outside integral first, because that's telling us what? See there, x is varying, correct? What are your limits of integration? So that means that in your region, x has to vary between 0 and 4, correct? Right? If you want to write that down on paper, right, you would just write this inequality x greater than or equal to 0, less than or equal to 4. So do all those pictures correspond to? Yeah, see, so that's not very helpful for us, is it? Okay, because aren't in all of these pictures x in all of these regions, isn't x ranging from 0 to 4? Yeah, okay. So they all match up, right? With the outer limits of integration. So that didn't help us at all. All right, so now let's look at the inner limits of integration, x to 4. So that means y is greater than or equal to x, right? Y has to be greater than or equal to x, but what? Less than or equal to 4. Well, let's see. I think in all of these pictures, y is less than or equal to 4, but where is it bigger than or equal to x? Well, where is the curve y equals x? Is this y equals x? I don't think so, right? Okay. Is this one y equals x? Yeah, this curve is y equals x. That line is y equals x. So that's a possibility. But this one also is a possibility, right? Because that also involves the line y equals x. So we can eliminate these two because this line is not y equals x. Y equals x is just 45-degree line. But remember, we want y to be bigger than x. So in which of these regions is y bigger than x? This one? Right, yeah. Take any point out of this region, right? Okay. And the x coordinate is going to be bigger than the y coordinate, right? So I'm sorry, the y coordinate is going to be bigger than the x coordinate. So in this region, y is bigger than or equal to x, right? So that corresponds to our correct limits of integration. So it looks like that's the region of integration. Now, unfortunately, if you try integrating this, what goes wrong here? Let's write this down. So, can y'all remember that for me? So what does that look like? Let's see, what was this, 0 to 4? So that was easy enough. And then what, x to 4? But the integram was a little bit not nasty, right? It was x times what? The square root of 1 plus y cubed? And then dy dx. So with this order of integration, you are that order of integration, right? Okay. You are you're going to have to integrate that expression. X is a constant, but you have to integrate this expression, the square root of 1 plus y cubed. Yuck. Any ideas on how to integrate that? Yeah, I would use substitution, but what's going to go wrong there, Elijah? Yeah, the problem is, so you were thinking of this substitution, so we could end up with u to the 1/2 power, right? Which is easy to integrate, right? Just using the anti-power rule. But unfortunately, if you take du there, right? Okay. I don't know if I should write du dy, right? If you take du dy, you get 3y squared, correct? Which means that what's dy equal to? Du over 3y squared? Or I'm sorry, what's du equal to? No, I'm sorry, dy is right. So you get du over 3y squared, is that right? Am I doing that right? And so when you substitute, you will get square root of u, but unfortunately for dy, you get this nasty du over 3y squared. So you see the y's have not dropped out, right? So now you have the x, of course, is still there, but unfortunately the y's have not dropped out. So now you end up with this expression with three variables in it. So you're really in bad shape. Okay, right. So substitution does not work there, unfortunately. That's the moral of that story. But the other moral of this story is switch the order of integration, because I think that's going to make things better. How can we switch the order of integration here? See, we were treating this as a vertically simple region, all right? That is a vertically simple region. The curve on top is y equal 4, and the curve on bottom is y equal x, right? So that's a vertically simple region, but it's also horizontally simple as well, correct? Right? You can also integrate in this direction. How would we change the limits of integration there? So that's what they're suggesting here at the bottom. Switch from dy dx to dx dy. Okay. So how do you switch the limits there? So y is second. So what's the range on y here for this region? Yeah, 4 is the upper limit, right? On the y-axis, you're going from 0 to 4. But now what about on the x-axis? We start at 0 and we go to this line. This is the line what? Y equals x. So that means we're going from 0 to y. Be sure you put y there, not x. Because you want your variable of integration here to be on the inside integral, you want it to be x. So that means you need a function of y for this upper limit of integration. Otherwise, you'd be having a variable, the variable x in your limit of integration. You can't have that, right? But here, since we're integrating with respect to x, y is a constant. See, x is going from 0 to y. That's going to make things easier to compute, because now when you're integrating with respect to x, you just have here what? X times what's this square root? That's just a constant, right? So how can you integrate this? Just using what? Just using the anti-power rule, okay? So the first antiderivative is just the anti-power rule. Well, I claim then the second integration will also turn out to be easy, okay? You may have to use substitution, but it will turn out to be feasible, okay? If you switch the order of integration. Okay, well, there's some hints on your on that homework. It's got a lot of problems. It's got 14 problems, which is kind of a lot. So there's a lot of integration there. I may set that back to Monday, do Monday, so we can talk about it again if y'all have questions on Monday before it's on specific problems before it's due. But make sure you've worked on it before Monday, because then you'll blow your chance at answering questions, okay, about the problems. Understanding this homework is kind of really helpful. So let's go back to we want to go back to the notes, because we were computing volumes last time, right? And we had just seen one example, but we had, that was a very confusing example. So I need to summarize that example. We were trying to find the volume of this prism. We can call it a prism. The volume beneath this plane. There's the formula for that plane. The volume beneath that plane down to the XY plane. Okay, bounded behind there by the XZ plane, and bounded on the left-hand side by the XZ plane, and bounded behind by the YZ plane. So you have kind of this pyramid shape, but it's not really a pyramid, right? Okay. It's kind of a three-sided pyramid, all right? But the key aspect of that pyramid, right, is it's below this, it's the volume below this plane, right? Okay. So last time we were learning conceptually how to apply double integrals to this situation. So I need to review that very quickly. We're not going to go through the whole explanation, right? Because that took a long time, but we're going to summarize that, right? And we're going to give the 25 words or less summary of that, which is really all you need to actually carry out the problems if you're still a little bit conceptually hazy on why what we're doing is actually working. All right. Okay, so let's take a few minutes though, because we're kind of exhausted. So um, so let's come back there about 12:45 and do some more examples of volumes. Okay. Okay, let's start again and let's remind ourselves of how we computed this or how we were attempting to compute this volume last time. We never actually finished the calculation, but we set up the double integral expression that if we had evaluated it, it would have given us the volume. Okay. All right. So our idea is as follows. So we've got this volume, right? Okay. The volume beneath this plane, right, in this prism. So remember what we did last time was we took a slice, right, out of this prism. I arranged this slice though so it was a parallel. I'm sorry, perpendicular to the x-axis. So this slice that I've drawn here, as you can see there, it's perpendicular to the x-axis, right? Or you can think of it as parallel to the back side of this prism, which is the YZ plane. Okay, so this is a vertical slice, right? Okay. Now I just position that vertical slice at some arbitrary value of x on the x-axis. So the x here could be, close to the y-axis back here, in which case the slice would be bigger, right? Or when you're up here close to 3 on the x-axis, if the slice were right there, the slice would be much smaller, right? Okay, so anyway, so there's the picture of that. There's the picture of that slice. Now, remember, what we're going to do is compute the area of that slice, because that slice is two-dimensional, right? Okay, I've just intersected this vertical plane with the prism to get this two-dimensional slice. So we're going to calculate the area of that two-dimensional slice. Now that's just a triangle, so we could, in this case, it's just a triangle. So we could just use some formula for geometry for triangles, right? For computing area of triangles. But we don't need that, because we can also use calculus to compute the area of this. This is a two-dimensional area, right? This is a two-dimensional area we're trying to compute. And it's the area, notice, beneath this line, right? It's the area beneath this line down to the XY plane here, right? Okay, so actually you can think of it as the area beneath this straight line, right, down to, you can think of this as being an axis. Actually, I guess you could think of it as being the y-axis, right? Because it's kind of it's parallel to the y-axis, right? So we're just computing an area beneath a curve, in this case beneath a straight line. So we know how to do that. We can use calculus to do that, right? The area beneath a curve down to an axis, that's so easy. That's just a definite integral, right? That's just a definite integral. So all I have to do is figure out, well, what are the limits of integration, right, along this axis? What are the limits of integration, right? And then I need a formula for this straight line, correct? And then I just plug those into my integral and I can compute the area of that slice. Well, let's see now. So how do I figure out what the limits of integration are here? We're going from where to where on this. We can sort of think of it as being the y-axis, right? Because this line is parallel to the y-axis. Well, where are you starting at? Obviously, on the y-axis, where are you starting at? What's this? See, this is for a fixed value of x, right? Because you fixed the x. So where are you on the y-axis? Are y'all lost there already? 0, right? Okay, you're 0 on the y-axis. And the question is, where are you going up to? You're going up to this point, okay? Now, we have to figure out, what is that point going to be? Well, notice that point is going to lie on this line. That is the intersection of this plane with the XY plane. That's called the trace, right? So you know this point is on the trace of this plane. There's the formula for the plane, by the way, with the XY plane. Well, you know how to find the formula for a trace, right? In the XY plane, you set the Z to 0. So we set the Z to 0. I just solved this for Y to make it Y equals equation, a linear equation, and I get Y equals 3 minus X over 2. So this point is going to be whatever arbitrary X we choose here, X, right? That's going to be the X coordinate. And then the Y coordinate we're going to get from this formula. So that would be 3 minus X over 2, right? Because that comes from the fact that this point lies on this trace, and there's the formula for that trace. Oh, so in computing the area beneath this straight line, right, this two-dimensional area between the straight line, I'm going from 0 to 3 minus X over 2. Oh, there's my limits of integration. Now the question is, what's the formula for that line, though, right? What's the formula for that line? Well, that corresponds to the formula for the plane, correct? Right? What's the formula for the plane? It's just 3 minus X minus 2Y, correct? Notice the height of that line falls on the that plane, right? What's the height of that plane? Well, the height is Z, right? And that's given by 3 minus X minus 2Y. Oh, so so I'm finding the area beneath this curve, right? 3 minus X minus 2Y down to the XY plane. You might say, why does that have two variables in it? Because remember, right? Okay, you're thinking of X as being a constant here, right? The X is fixed. So you really only have one variable here. You have 3 and you have 3 minus a constant minus 2Y. Y is the variable. Y is what's varying, right? Because we're varying on the Y-axis from 0 up to 3 minus X over 2. All right, well, that's all well and good, but all that gives me is an area of one slice. I want a three-dimensional volume, correct? So how do I get a volume out of this? That's easy, right? You're going to take these slices over and over again, correct? From front to back. The way of computing the areas for all of these slices is the same. It's just like this, correct? But now what do you do with all those areas? So here's where the calculus part comes in. You take all those infinitely thin slices, right, which have areas, and you do what? You add them all together, right? Okay. So you're adding infinitely many infinitesimally thin slices. That's integration. Okay, right? So we're integrating all of these areas together to form a volume. Well, how many of those are we integrating? Well, there's infinitely many, right? But where are the infinitely many located? They start where on the x-axis? Because you want to go front to back, right? You want slices all the way from the front of this pyramid to the back of this pyramid, right? So where are we starting at on the x-axis? On the x-axis, 0 going up to where? 3. So we take all of those areas, right, and integrate them from 0 to 3 on the x-axis. So you get this double integral as representing the volume. Now, we talked last time, of course, more about why what we're really doing geometrically, right, when we're doing the double integration. Of course, we're not really adding together infinitesimally thin slices, right? Okay, we're adding together slices that really do have volume, but then we're thinking about what happens when the slices get thinner and thinner, right? Okay, so we're actually taking a limit, but ultimately that limit turns out to be this double integral. So we can think of it as adding together infinitely many infinitesimally thin slices. That's really useful. Especially when you're doing double integration. Look, here I sliced the prism from front to back, but I do not have to slice it from front to back. I could also slice it from left to right. Let's set up the double integral if we took the slices from left to right. So you see that little green triangle? That's a slice where we took a plane that was perpendicular to the y-axis or parallel to this face of the pyramid on the right, on the left-hand side, right, and sliced through the volume this way. Okay, so we could also take infinitely many slices from left to right, integrate all of those, okay, and also come up with the volume. Let's see what the double integral would look like in that case. All right, so what we have to do is find the area of this little green triangle. All right, we're going to do it with an integral. Okay, so let's see what that integral is going to look like. See if I can squeeze that in here somewhere. Maybe y'all can help me with this. All right, so let's see. I bet I can. So we're going to first calculate the area of that green triangle. So let's see. That means I'm going to find the area beneath this green line. By the way, what's the formula for that green line? It's the formula of the plane again, right? Okay, so you just use the formula. I forgot what it was. I can't see it there. 3 minus x minus 2y, right? Okay. What's going to be my variable of integration here? Dx, right? Right, because x is going to be varying, right? Notice you're starting from the y-axis going forward on the x-axis, right? When you're integrating to find this area, where does the x start at there? 0. At the back, it's 0, right? And where does it go up to? Oh, what is this point? That's right. So remember, you're fixing a y value when you take this slice, right? Okay, so you know your y is whatever y value you fix. You have to find the x coordinate in terms of y. Okay. Let's go back and see if we can. Let's go back and see if we can figure that out. So what's x here in terms of y? So look at the trace and solve for x. Oh, that's pretty easy, right? Because you can just shift the x over. So you get x equals what? 3 minus 2y? Oh, I like that. So that doesn't have a fraction in it. So there I have just 3 minus 2y. That gives you the area of the little green triangle here. But remember, we're going to find areas for infinitely many of these slices, right? And then integrate all those areas together to form a volume. So that's easy, okay? We're just integrating all those slices together. The area of all those slices are computed the same way, right? Except what's changing? The y, right? Okay, the y in this formula is changing, and it's changing from what to what? 0 to 1.5, right? So there's the second version of the double integral for computing that area. I think if you so I think this one is easy. Well, maybe I'm wrong there. They're both a little bit cumbersome. They involve some clumsy algebra. So I don't want to go through all the calculations of computing the double integral. There's nothing difficult about the integration, though. Okay, it's all straightforward integration. I think the answer comes out to be 9/4. So we could maybe check that with Wolfram Alpha here if we don't want to go through all of the steps. So I think that's the volume is 9/4. Woo, wow. Okay, let's try another one because one example ain't gonna be enough, right? Oh, I want to point out because this is important to us in the future. I did slices that were parallel to the back, right? So we started with these slices that were parallel to the back of the prism, right? In other words, parallel to the YZ plane. And then we did this bright yellow, bright green slice, right? Those are parallel to this face of so on the left. Right? But I could have also sliced this out I'm missing one top to bottom, right? So I could have picked slices. I could have picked slices that were parallel to X, Y. Okay. So slices that are parallel, probably going to screw this up. Slices that are parallel to, yeah, well, maybe not like this. Yeah. Okay. So slices that are parallel to X and Y. Now that is kind of attractive. Do it that way. Notice, but you're really just is a going to compute an area, like the slice, and integrate all the areas up to the top of prism, right? Okay, but those are really you can really think of those as areas in XY plane, right? Because all of these planes are parallel to the XY plane, so you're sort of computing an area in kind of in the XY plane, correct? In fact, one of them, bottom is indeed sitting directly like all the other ones parallel to the so in XY plane. But just learn how to compare areas into XY plane. Because we do that using what? Double right. Yeah. So we this area using a double. That's just an XY plane. What's the integrand? XY plane. Maybe it's at home. What'd you say, Robert? If you had an area in XY plane using a double integral, your integrand is just one, right? Okay. Integrand is just one. So we can compute these areas and think about it carefully. Integrand of one, but then how do we find all those areas together? We have to integrate again, right? We have to integrate again from top to bottom. In this case, from what? Z equals 0 up to Z equals 3, right? Okay. We have to integrate all of those, that area together. Cool. That means we have double integral to area and another integral to compute volume. So you're going to end up with how many there? 3. All right. Okay. One for each variable. So you'll have dx, dy, and also dz. Okay. If we try it that way. Well, let's not try it that way. All right. But there's an idea that we skipped over, you see. Okay. All right, let's try another just double integral. So I have a lot of steps here. I didn't fill in all the steps. Oh, by the way, I wanted to point out sometimes it's really helpful to draw your region of integration. The region of integration is the region in the XY plane that your volume is sitting on top of. All of these problems are volumes above the XY plane down to the XY plane. So sometimes it's and so that where that volume hits the XY plane, the trace in the XY plane is the region of integration. And sometimes really helpful to draw that separately. That sometimes helps you understand what you're doing. We didn't really need to do it in that case because the picture was kind of clear here without drawing the region of integration separately. Let's try another one. Maybe it's also easy. So here's my second example. So I want to find the volume beneath this surface. So that's some sort of quadratic surface. Don't know what it is there. Down to the XY plane as shown here. Oh, so let's describe our region of integration. But this is a nice region of integration. Your region of integration is just what? It's just that square, right? Okay. So we don't have a complicated region of integration. So we like that one. If you want to describe that, you can describe that in using inequality. So this is x is between 0 and 1, and y is also between 0 and 1. Okay. All right. but the so nice region of integration. So that's probably going to make the limits of integration easier to understand, I think. All right, now, but the idea is the same. We're going to take a slice, right? Okay, a vertical slice of this volume. Remember, we want below that surface all the way down to this square in the XY plane. So you have a solid there. I just don't have it drawn as a, just don't have it drawn as a solid because that makes it harder to understand. So we're going to take a slice. So you can take a slice that's perpendicular to the x-axis, so a slice like this, or if you want to, you can take a slice front to back, right? How do y'all want to, what do y'all want to try? Left to right? So that means just fix some value for x, okay? And take a slice out of this thing. Let's see if I can draw this kind of. So we're going to have a slice of, I'm fixing a value for x. So, so I'm going to, so the slice is going to intersect with the XY plane of this, right? It's a nice straight line. The XY plane, that would be a vertical, right? It's fixed. And let's see, so then let's draw this up. So I think it hits that. I think it hits this grid on the surface. So, oh shoot. No, I missed completely, right? So there's kind of what our slice, kind of what our slice looks like. Then you complete the area of that slice, and then integrate, right, all of those areas together from front to back, right? And that should be small. So what's that double integral going to look like? Let's do the outer first because that one's so easy in this case. So what are the outer limits of integration, right? Are that's the integral where you're combining the areas of all of the slices. You're not computing the area of each slice, just combining the areas of all the slices that are already right. So just 0 to 1, right? Okay. Just going 0 to 1, right? On what axis there? X-axis, right? Okay, see from front to back, all of these slices, right, that are perpendicular to the x-axis, we're creating all of these together. So that would just be 0 to 1 on the x-axis. So that tells us, of course, that the outer variable of integration is dx, right? And then the inner integral is going to be the area of the slice. So that's the one that's usually, if it's going to be tricky, that's the one that's a little bit tricky. So how do y'all find the area of this slice? So that's just the area beneath the curve, right? Just the area beneath the curve. So we're going where on the y-axis? Going across to where on the y-axis? Fine, that's easy. But the question is, what is the curve? That's the part that should be pretty straightforward. That just corresponds to the surface. That just corresponds to the surface. And if you have your surface written as z equal to some function of x and y, you can just use that function. Just straightforward, put that in. So it's not complicated at all. You must have z equals 2, though. All right. If you have your surface where your variables are a little bit jumbled in the equation, be sure you solve for z. So I'm just going to take all of this, the 1 minus 1 half x squared minus 1 half y squared, and just fill all of that in there. So let's put that in 0 to 1, 0 to 1, 1 minus 1 half x squared minus 1 half y squared. Should give us the volume. It's very easy to switch now the order of integration here if you wanted to arrange your slices from left to right. So if you wanted to make your slices so that they intersect with the xy plane like this, that would be a horizontal line in the xy plane. Then all you're really changing is the limits of integration. This formula stays the same, but here, well, the limits of integration are still going to be 0 to 1 cases. So changing the order of integration doesn't really change much in this particular situation. Shall we calculate that? Oh, I don't know if we have time. So we'll have to save that computation for next time. Ooh, let's look at one more. Yuck. So that surface is e to the minus x squared. I have a feeling that's not good. Okay. That's not our problem at the moment. Just want to see if we can set up. Just want to see set up the double. All right. So, but here the region of integration is not quite as simple as in the prior example. This little triangle is going to be so we want area beneath this surface, just above this triangle. So that's the triangle defined by well, z equals 0 is the xy plane, so that's the bottom of y equal x is this line, x equals is this line, right? So we want beneath this surface, e to the minus x squared is the for that surface, just above this little okay. So how do y'all want to slice that? You want to go left to right or front to back, or how about left to right? Maybe that's easier. So let's try a slice like this, okay, whose trace in the xy plane looks like that. So you're fixing a value for x, right? So and so you're going to form, these vertical slices from front to back. So what's the outer limits of integration? Got 0 to 1, right? Okay. So you're going to form a bunch of these slices, right? Starting at 0 on the x-axis, of course, that slice is empty, right? But as you come forward, slices start to have correct. Up to x is 1, you'll have slice. Okay. This plane. So you're just going 0 to 1 on the x-axis. All right, so that's pretty easy. And now, what about though computing the area of each slice? So that's going left to right. So where are we starting? Starting on the y-axis, because dy is going to be variable integration, right? Y is what's going to vary. Starting at 0 on the y-axis and going up to this line, which is x. Sure to write it in terms of x, right? Okay, this is the line y equals x. That's the curve y equals x. But in your limit of integration there, be sure to write x, right? Because if you write y and variable integration is y, then you have your variable That's not possible. Can't have it. It has to be a definite interval, but well, never mind. Okay, I'm gonna confuse things. So it's what, 0 to what? X, right? And what's my of course, what's the formula for the plane? There you go, e to the minus x squared. So if we can figure out how to evaluate that, right, then if we figure out how to evaluate that, then well, right. So let's come back and look at those. Any of those are easy integrals and make them hard. Actually, okay. But remember, we've always got Wolframs to help us do that, right? If we get stuck. Okay, so let's let me sign. Let me have you sign that. Sign that, and I'll see you guys on Monday. Hmm? Yeah, so yeah, that's right. So next Wednesday is no class, right? So probably the sample test, yeah, sometime next. Right. No, it's actually yeah, because we have a full week after and a Monday. That's on Monday. So I have 3 days. Yeah. Okay. You got it. That's right. Yeah.